Okay, that's working. All right, I'm going to start the webinar, and you can just wait till the attendee list goes up. Okay.
All right. Welcome everybody to this session. We'll just wait a few moments for everybody to file into the room, virtually speaking. And so welcome to session 7. I think people are largely here. I'm Elsie Kaiser, and I'll be serving as the session chair for this session. And I'll just go over a few quick reminders that you have probably already heard earlier. If you have a question for a speaker, you can send it at any time by using the Q&A button and by entering your question. And if it gets selected during the Q&A, I'll call you by name and you'll be invited to unmute to ask your question. Or if you prefer, I can also read the question for you. So please indicate that if that's your preference when you submit. So let's get started. And I'm very excited to introduce the invited speaker for this session, Linda Smith. She's the Chancellor's Professor of Psychological and Brain Sciences at Indiana University, where she directs the Cognitive Development Lab. And Linda Smith has received many accolades and awards for her research, including the Rumelhart Prize in Cognitive Science and the William James Fellow Award from the APA, and has done really groundbreaking work on infant development in language, perception, and action. And one of the central issues in her work is looking at the mechanisms of change involved in the development of these domains and how they support language learning. And her work is characterized by looking at multiple components and multiple timescales, both millisecond by millisecond, processing effects, as well as developmental changes over months. And today she'll be presenting a talk entitled Discourse with Few Words, How Infants Form Durable and Expressible Memories of Objects and Their Names, which is work with Harar Raz. So thank you.
All right, hello. I'm very happy to be here. All right, so before their first birthday, before infants say many, if any words, they know some object names. We know they know some object names because when experimenters play a word, play an object name, they sometimes reliably, more often than expected by chance, look to that object. This is fragile in children before their first birthday and right after, but it's highly reliable, replicated many, many times. But the field has no understanding at all as to how infants actually manage this young, how they manage to learn those object names. The founding assumptions for just about all accounts and experimental studies is that infants learn these first object names through ostensive definition by linking co-occurring heard names and seen things. There are two fundamental problems that many, many, many people have noted about in terms of explaining just how they managed to do it. One problem is referential ambiguity. There is just lots of nameable things out there in the world for infants who don't know any names yet. How do they know which object they should be linking the name to? So for example, in one of our studies where we did day-long head camera recordings, we just counted up the number of nameable objects with common everyday basic level names. And your average image has 10 to 12 objects or so in it that it could be named by somebody to the baby. The second problem is the infrequency of any individual object name in parent input. We know the parent input matters mostly through measures of aggregate. So the more frequent parents talk, more likely the higher early vocabulary is. The more co-occurrences between what parents say and the objects in view, the better the vocabulary. But when you get down and try to look at individual object names, they are absolutely very infrequent. Any individual object name is infrequent, and we're just completed a study in which we've shown the same thing, but we're not new at noting this. So again, it was a head camera study, and we looked at day-long audio and video recordings, and we looked at 90 meal times for infants 7 to 11 months of age. And we asked, let's take the objects that are most prevalent, that are actually objects that are on the MCDI for early learned object names. And we only looked at those objects that were at least visually present 50% of the meal times. So they're really common at meal times. Parents hardly ever named them. That's what's shown on the graph over here. Out of the 90 meal times, the most frequent objects weren't even named in 25 of them, not even once, okay? They're just not frequent. This may seem odd to you, but parents don't talk. They do talk. Parents don't name objects to babies who are under 12 months and not talking much. Instead, they do things like say, hey there, sweetie. Oh, is that good? Oh, you're a sweet baby. But they're not naming the objects. So how on earth do these infants learn these object names? Well, one of the things that motivates much of my approach to work is this idea that we really should be studying the learning machinery and the training data for learning together. Not making assumptions about it, but actually going out there and trying to understand what the structure of the learning environment is, and then trying to line that up with what we know about potential learning mechanisms. And that's what I'm going to do today. And the basic idea we have is that since object names are pretty infrequent in these young learners' environments, and since co-occurrences are therefore infrequent in these young learners' environments, then we need to look beyond co-occurrences for other aspects of the learning environment that may support rapid learning. And our approach here was really motivated by this paper by Ann Tyler, in which I think she had a very nice perspective, analytic perspective on what makes conversations coherent. And what she says in that paper basically is that conversations have topics that are repeated and other elements that are not really the topics themselves that are also repeated and that are shared. Sort of shared patterns keep coming up over the course of the conversation between the participants. And she noted that new information comes embedded in these stream of events with a temporal structure of lots of other repeating elements, okay? So what I'm going to talk about today is what I think is a new solution to how babies break into object name learning. And I'm going to talk about a conversation, you can think of that as in quotes, a conversation of actions in which there are repeating elements. Those actions are repeating elements to those actions, and they're rarer new information, the occasional object name said by a parent, occurs. And the basic idea is that repeated and parent-infant shared actions on objects that surround these rarer naming events, they are what make object names learnable from very little input, very few naming events. All right, so here's the structure of my talk. I'm going to first present you an observation. This is observations of parents and infants that over extended durations of everyday parent-infant social interactions, there are repeated and shared actions on objects and that these surround the much rarer naming events. Then I'm going to present a little bit of theory. The theoretical idea is that the temporal multimodal structure of these social interactions aligns with contemporary understanding of rapid cortical memory formation, the kind of rapid cortical memory formation that does not involve the hippocampus. Third, I'm going to present a model. This is a mathematical model. I won't spend too much time on the math, that shows that these processes form strong memories, that I can input the data from the individual parents and children observations that I talk about in part 1, and show that actually name-object associations are quite learnable, giving these processes from very few individual naming events. And then in a very brief discussion, I'll talk about why we should expect the statistical and temporal structure of experience to align, of infant experience to align with the properties and principles of fundamental cognitive processes. All right. So for the observation, here's the context. We took parents and their 12-month-old infants, and we put them in a room in which we dumped 33 toys on the floor. The baby wore a head camera and a cap and recorded the events. We also had a third-person camera. The parents were not told we were interested in naming. They were not told we were interested in much of anything. We just said, we want to put you in the room for 10 minutes with your baby. Just keep them happy, okay? Keep your child engaged and happy any way you want, okay? They didn't even have to play with the toys if that's what they didn't want to do. What we measured, oh, and the other thing to note is the toys were a haphazard collection. There were no themes. They just looked like your average huge variety of toys dumped out of a toy box. Our measures were parent and hand actions on the objects and the object to which the action was directed, and parent naming. Okay. Now, by one description, this context in which we put parents and children, 33 haphazard toys on the floor, no instructions to do anything, was a poor context for learning name-object co-occurrences. The mean number of naming events in 10 minutes was 36, okay? 36 total naming events on average, and that was distributed across 10 different toys. The mean number of objects in view during a naming event was 10, so they were highly cluttered objects. How are these babies to know what any of these few names were referring to? And I put the graph up here, the number of objects in view. It's true for naming too. The patterns, the temporal properties, did not vary over the 10-minute play session, okay? That is, views were always crowded, pretty much, and namings were sort of intermittently here and there. All right, so that's by one description. By another description, this event is temporally structured as a coherent conversation of shared actions. So what I'm showing here is a time series. This is not actual data. I'm going to show you actual data and time series in a minute, of the actions where parents put their hands and where infants put their hands. And what you can see that I'm trying to illustrate here in this sort of representative one, I'll show you real data in a minute, is that there's kind of this joint activity. There's a little play from the parent with the child with the red object that we're indicating by red. Then the parent plays with it, then the child plays with it. Then they go off and do some other things for a while. They come back to the red object. They explore the green object. They, do some other things, come back to the red object. There's clearly sort of a shared kind of topic that's being repeated, and they're moving on and doing other things as well. And as representative of our data, parents name these objects quite intermittently, okay? Not commonly. They were not commonly naming them, but they did name them sometimes. All right, so first let me talk about handling. On the very first graph, I'm showing the frequency with which children handled individual 33 objects. And what every child showed was a very skewed distribution in which a few objects were played with a great deal. And many other objects were handled rarely. They were handled, but rarely. Different children, the popular object for different children was different, okay? So one child, the popular object might have been a little dog. For another child, the popular object might have been Mickey. But what I'm showing here is the mean frequency of the most popular toy across the children who participated down through the 30th, okay? And you see a very skewed power law kind of distribution. The mother, the parent, could have been the father, the parent shows the very same kind of distribution. A lot of handling of a few objects, much rarer handling of all the rest. And the other really important thing is the relative frequency or relative rank of handling of these 33 different objects was tightly correlated within the dyad. The most popular object was the most popular object, okay? And so the mean correlation, in fact, between the rank order for the parent and the child over all the dyads was 0.92, and within individual dyads, it ranged between a correlation of 0.81 and 0.99. Whatever the child is handling, the parent is handling. Now, they're not at the same time. These are back and forth, the topics of this action conversation. So here's actually real time series. I'm only showing the handling of the top 3 objects. All the other objects are illustrated in gray, just so that you can see the structure. But you'll see these are 4 individual subjects of the set. You know, so played with not the most popular objects. Then though the handling here is both the parent and the child handling, not separately, just whoever. So this red line here might be a parent handling, and that might be a child handling. But the dyad interacts with the red object, then with the blue object, then some other objects interleaving, then the red object, then some other objects interleaving, then the green object, some other objects interleaving. And as you can see up here, are the naming events. The naming events are definitely associated with these little clusters of activity, okay, with particular objects. But they're not on the whole. Here they're pretty frequent, but they're not, for most of these infants, they are not frequent at all, okay? So the other thing I want to say about this is that if you look at the naming, which occurs rarely, but close to these clusters of parent-infant handling activity, you see a structure in terms of the temporal properties that is bursty. That is, you have a little red activity, bunch of activity close in time, some spacing, then later on a repetition of that close in time activity, naming, parent handling, child handling, with the object indicated in red. And if you look at the number of clusters for the top 3 objects, they were on average in the 10-minute play period that they came back, little clusters of activity, to the top 3 objects 6.5 times. For the other objects, they were often repetitions almost 3 times on average. And the number of repeated events within a cluster, close to 5 for the top 3 objects, close to 3 for the others. And the average durations, 15 seconds, 18 seconds of these clusters, little clusters of repeated activity throughout the play. So what does this conversation of actions look like? What we have is a few topics that recur throughout the interaction, and a temporal pattern of close in time repetitions around one topic, and over longer delays, repeated clusters of activity directed to that same topic. This structure actually lines up with a well-known statistical and scale invariant property of human behavior. That is, we have a power law frequency distribution. Don't play with everything, but you select a few topics and then other things occur in around those topics, and bursty temporal structure. Okay. All right, now into my second part, okay, the theory. So the complementary learning system theory of memory formation, proposed by McClelland, updated a few times, suggested that there are really 2 basic ways in which memories are formed. One is what we think of the rapid formation of episodic memory using the hippocampus and that playback system. So the hippocampus, what's shown in red here in the little picture of the brain, is rapid learning of connections and any kind of arbitrary information. And then the green connections, okay, there's direct cortical learning okay, without much involvement of the hippocampus. And that was, is thought or was thought to support gradual, slow, incremental structured knowledge. Okay? Slow, gradual, incremental, lots of data, okay? And then when we get, there are connections or interactions between these two. But this basic understanding of how memories are formed has always been sort of a problem for understanding how it is that infants so rapidly or seem to learn about their world and about the reference of words. Because if it's gradual, that should seem to mean a lot of data, a lot of repetitions, high frequency. And as we noted, it doesn't seem to be quite so clear that there's such frequent naming of individual objects. And that's problematic because the hippocampus is not mature until about 2 years of age. Some doubt that it's functioning much at all or that it's playing a very big role in early learning in infancy. I have this paper down here by Turk Brown because he's working very hard on trying to answer those questions, and it's certainly not clear if it might be contributing a little bit, but the evidence isn't very good that it is, okay? All right, so then how is memory formation happening? Well, lucky for us, there has been recent advances in the study of cortical learning without hippocampal involvement. And cortical learning without hippocampal involvement is definitely available to young babies. And this work, mostly from animal research, suggests that you can get very rapid, through cortical processes alone, without hippocampal involvement, formation of durable and expressible memories. Almost, really very rapid formation, very few instances, minimal experience under certain contexts, okay? That the to-be-associated items emerge from just previous and influence future actions. That is, that they're part of some kind of predictive sequence of events, okay, in which what happened in the past is temporally related to what happens next. That the to-be-associated items emerge within a social interaction. These are mostly social interactions of mice, but nonetheless. That the context is multimodal, and that is that it recruits activation across many different neural networks, okay? Across many different parts of the brain, many different, those green parts all at once. And that the associated items are repeatedly activated through partial completion, through pattern completion. That is, when you have complicated multimodal events, some parts are there at one moment, other parts are there another moment, and so you have this pattern completion which strengthens the binding between them. The idea is that these kinds of properties, the reason why they work to lead to rapid memory formation, is that they result in persistent activation across the cortex, sort of reverberating, enduring activation over minutes, okay, that lead to rapid, durable memories. And this persistent activation has been shown in a variety of studies to support one-shot learning of novel associates. So if you have some event going on and a lot of persistent activation, if some new piece of information comes in about that event, it gets integrated into the memory and is there. One-shot learning, okay? Now, if you think about what I just told you about these parent-infant interactions and their nature, they seem just like these events, which experiments show lead to rapid memory formation from minimal experience. That is, they're in a task in which they're playing with an object, their mom, that influences their mom to play with it, which influences them back to play with it, a series of organized events, repetitions in time, out of each other influencing other. These associations emerge in a social interaction that have all that extra neural activation that comes from being in a social interaction. The context is multimodal. There are seen objects, there are heard voices, the toys may make noises, there's emotion. And the associated items can be repeatedly activated through pattern completion. So we have, these objects named here, but when they're activated, again, when you're looking at the object here, nobody's talking, it should activate those prior memories. Okay, that's what they mean by pattern completion. And the idea is that all this for the baby, like the animal studies, will result in persistent activation and durable rapid memory formation. And the few shot learning of the name for this red object, only 4 naming events, but maybe a permanent name because it's embedded in the persistent activation through the conversation of actions. All right. So now the model, and I won't spend too much time on this and the math parts, but what the basic thing we want to model and ultimately make individual predictions about individual children and individual object names is we want to model, excuse me just a minute. We want to model the momentary activation at every moment during the play of each object's memory and its name. And then we want to evaluate, so that we can evaluate the persistence of activation given the properties of the social interaction. So what's the nature of this model like? Well, our starting point is well-documented, law-like, and highly conserved spacing and repetition effects in human and animal memory. And these have been well modeled since Ebbinghaus. I put up some references to newer models, which are, their math is closer to our math. And basically we start with these kind of basic ideas about how memory strengths change with repetition and with spacing between repetitions as our starting point. We do something a little bit different in these models in that most of the classic models are trying to look at retrieval, what happens when you go in at a moment and test them. And we don't really want to look at retrieval strength. We want to look at the momentary activation because we care about persistence of that activation. Basically, the basic ideas of the model are these, is that momentary activation for any individual object, name, memory, at any step in the play is equal, its strength is a function of the previous repetitions and the time delays between those repetitions. And repetitions have bigger effects the farther away in time they are. Two things close together, that'll keep the activation going. But if you've had an activation and then you have a repetition farther in time, it actually gives a bigger boost, okay? That's the well-documented effect. The effect of time itself, everything is weighted by history. This is really a dynamical system. What's ever happening at one moment in time depends on the previous history, all the way back to the beginning of the play session, okay? So the effect of time itself is weighted by the history of elapsed times between repeating events, and the decay rate, how much memory falls down, is also a function of the history of elapsed times. And what we add to the standard sort of models is based on contemporary understanding. We've tried to put these ideas about contemporary understanding of rapid cortical memory formation into the model. So we're looking at momentary activation. Our math is just slightly different, not retrieval strength. And one of our key measures is going to be the persistence of this activation over extended time, over the whole play session. We're just doing a very simple thing right here. We're just going to sum up all the momentary A and call that our persistence measure. And we are going to combine the multi-element components in the memory strength. Okay, this is sort of the new idea. Whoops, let me go back here. So here we have a series of head camera images. You know, there's the dog, mom's playing with the dog. Mom's got her hands on the doggy all the way through here. That's a doggy. And she names it a couple of times, okay? By our model, this, whoops, why do I keep hitting that? By our model, okay, the memory for the dog starts forming. So there's a little bit of activation, persistence in time. At this point, mom says doggy, the word gets incorporated in. And now through all these continuing activations, because the doggy was incorporated into that moment, the persistence strengthens not just what's happening at the moment, the sight of the doggy being shooken by mom, but also the word which is connected to it, okay? All right, so the memory's a whole, and when little things get put in, they get integrated and they get strengthened in this extended persistence, okay, period of persistence. So here's what the outcome of the model looks like. Here are the top 15 objects, I think, being modeled for individual children. And here on the big thing is the mean for the most frequent to the least frequent objects. And as you can see, the red to orangey ones are the most frequent, and the green are kind of middle, and then the purple and pinks are the less frequent objects. Frequency is not a great predictor, okay? That's because the temporal properties matter. You can see this in cases over here where we have individual children. So here's this kind of yellowy object that they played with in the beginning, and the spacing between how often it was played with, I think it's like about the 4th most frequent object, has the highest consistent persistence of activation across the whole play. You can also see you have this child over here where you have a few objects which have really persistence over the whole play period, but most do not. That has to do with the temporal structuring. And if you play with one object, then play with another object, then play with another object, the memory strength, the persistence of the activation won't be so good. But if it's like a conversation where you do something with one object, add new knowledge, go back and relate it to the previous, add new knowledge, go back and relate it, then you're going to get cases like this child here who really, the persistence and activation for all of the objects and object names is really quite high, okay? This just shows you the P for the objects most frequently played with to 15th most frequently played with object out of the 33 for each of the individual children. And you can see these are each dot is an individual child here. This shows even more clearly that the persistence value is not really well predicted by the rank frequency of the objects and their names, okay? Because the properties that are making durable memories by this model aren't simply frequency and aren't simply co-occurrence, okay? It's a persistence over time in an organized, coherent play. All right, so this model needs to be tested. We are sort of in the process of doing it, got a little disrupted by COVID, so. But we have begun, we're testing it, okay? But I want to say something about the implications that this model proves to correct, okay, for how we think about early object name learning. First of all, it suggests that clutter in the world and ambiguity may not be all that important in terms of predicting early object name learning. What will be more important is the clarity in the moment of what we might be thinking about. That is the activation in the head. Okay. It also suggests that co-occurrences of objects and names may not be important as the temporal patterns within conversations. Okay. For young children, those conversations are going to be joint actions because they don't talk yet. Okay. Later on, those conversations are going to include other words, and those properties may be way, way more important than simply the frequency of the word or its co-occurrence with a reference at that very same moment. It also suggests that early object names are, in principle, learnable from a single context with 2 to 3 naming moments. Just what we all sort of know happens. You go to the museum and you talk about the cougar 1 or 2 times, and the child seems to know cougar, okay? This would be an explanation of how it is that that happens, okay? All right, so I began, this is not in my discussion, and I'm coming to my end right on time. I think I just heard my warning, that we should expect, okay, this is just one example where we look at the structure of the larger context, not a priori ideas, but actually try to look at the learning environment itself in its own terms, what the structure is. And why I think that's, one reason why I think that's an important property is this idea that the temporal principles of experience, especially for young infants who we know just rapidly learn all kinds of things, has to align with whatever the properties are of the learning mechanism. And so, Tyler, I began with this point that, conversations have topics, repeated elements, shared patterns. And what I'm suggesting is that in the shared patterns of joint action, conversation like joint action between parents and infants, that they are building internal events which make learning object names easy, okay, relatively easy. And so we might want to ask the question, why do conversations have this property? Well, they have this property because we have the same basic kind of memory system that infants do. When we're having a conversation, when we're thinking, what we're thinking about at any given moment depends on what we were just thinking about. It always emerges out of just where our brain was. And because what we are thinking about is influenced by what our conversational partner says, okay? We influence them, they influence us. And these activations are not, spike trains, they persist. And their persistence is a function of both their repetitions and the delays or spacings between those repetitions. That is, in our kind of, we're megalomaniacs, Hadar and I, we kind of think we're going to be able to model parents using these very same formulas, like what should their state be and how likely should they be to name an object, okay? Because it's going to be the same kinds of internal processes in the mom generating the behavior. So that's the idea. So I began with this idea that learning depends on both the learning machinery and the training data, but this kind of presentation treats them as separate kind of phenomena that should align, but how do they align? And what I'm arguing is that it's the same machinery in parents and infants that makes the social context in which the data for object name learning emerges. And that learning machinery is the same learning machinery that does the learning, okay?
About 2
There
minutes.
you have the two brains generating the learning material and the baby's brain through persistent activation that they generate, rapidly learning it. All right, so there, I'm at my end, I think. And I'd like to thank everybody in my lab who contributes greatly to everything, and especially to Hadar, who this is really her work and her model. And I'm ready to take questions.
Thank you very much. And so as a quick reminder, people can type their questions into the Q&A. And I also would like to also invite questions from students and postdocs and early career individuals. You can also indicate that when you pose your question. And we have actually, we have a lot of things happening in the chat. Let me start. I think the first one was Hayaka's Mangardic. Would you like to unmute yourself, or should I ask the question for you? So perhaps I will ask, the question is, if you could comment on what attentional systems underlie learning from structured and patterned social interaction.
On the attentional systems?
Yeah, which attentional systems might underlie?
There's a lot of work, and I'm actually very interested in this work on issues of sustained attention and the social, the role of responsivity and social behavior of parents in supporting sustained attention, which is been linked to learning object names or learning anything really about objects, about visual objects. And so I think that is highly relevant. I don't know what he means by the attentional systems. There's a lot of interesting work out there, really rapidly emerging stuff. I would strongly recommend the work of Dima Amso and her group, which have been relating early sustained visual attention to later developing executive function. And I think she has really very interesting ideas about what the role of the social interactions are in that. I don't know if that's what this individual is referring to.
Thank you. And So next we will go with Dan Swingley. I think you can unmute yourself or will be unmuted if you would like to ask your question.
Sure. Can you hear me?
Yes.
Okay. Hi, Linda. That was great. So I have a question for you. I'm sure you've thought about this, but classical memory models don't worry too much about the identifiability of the elements, right? So if you're Ebbinghaus and you can read your own handwriting, you know when you're seeing your own syllable again. Do you think that the fact that parental speech is phonetically a mess and that categories might be hard to identify would affect temporal aspects of the modeling? And my guess is that immediate repetitions might be more useful than the model would predict, but I'm not sure.
I'm not sure. Okay. So I've been thinking that, I think it's a really good question, but I've been thinking about the model in the sense that even though the standard classical memory models here that we're building on really show spacing is critical for the amount of boost you get from any repetition, I think that there's also a way of quantifying how those close and clustered time events are making persistence happen, okay? And that the fact that it's clustered, that your ideal learning for these babies would not be all far spaced apart. You really want that bursty structure, okay?
Yeah.
Thinking about memory. Now, it's also the case that when I think about this in terms of the memory models that are done with animals and memory, these may not be really precise memories, okay? So I think about, the generalizability that, the sort of not clear necessarily phonemic patterns or phonetic patterns that babies are pulling out, okay? That's related to some of your work, but also, Bergelson's and some other people's recent work suggesting you have really sort of rapid generalization on the visual side as well. That would suggest that these are not like snapshot memories, do you know what I mean? But they're going to be, but which also makes sense in terms of the fact if you think of them as reverberating, emerging from a lot of different components that are all sort of supporting each other, I think. Does that make sense to you?
Sure, I think so. I think part of the value of the burstiness might come in having a memory that's going to let you identify that something is happening more than once, in a
Yes.
short span.
And
you might not be able to tag it with the right category, either phonetically or as an object, if you don't have that repetition, just like structure coming out of the muck in a way. And maybe that's part of what makes the burstiness important.
I think that's plausible. I was thinking it was more amorphous, but the elements may not be well divided up in these kinds of memories.
Sure.
But
it's
a question.
I think we have time for perhaps one or two more questions. So let's go with Elika Bergelson. I think you will be unmuted if you'd like to ask your question.
Thanks for the very nice talk. I think about many of the same kinds of ideas. So I'm very curious to hear a little bit more about how you think of what gets to count as high frequency and how age plays into the story. So to say a little bit more, we do find that 6-month-olds, how much their parents engage in this referentially transparent kind of way does map onto those same babies' word comprehension in the lab. But you're right that it isn't as high as one might expect, but I find it a little bit hard to figure out what we should expect. What is high frequency? And related, just to finish the thought, that might be different for a 6-month-old versus a 12-month-old versus an 18-month-old, and something like one-shot or few-shot learning might be a lot more viable for an 18-month-old than for a 6 or a 12-month-old. But I'd love to hear your thoughts.
Okay, so co-occurrence is actually quite high, because co-occurrence is always done from the word side. If the word is it's a conditional portion, right? Given the word's there, given the word was said, is the object there, okay? And almost it's pretty high when measured that way. But so you could have a co-occurrence where a word has been uttered twice in the child's life, okay, and the object was there both times, but the raw frequency for that word is very, very low. Most of the work, I think all the work that I know of, and maybe I've missed something and you can tell me, where people have shown that the quality, the frequency of co-occurrences for parents, or the frequency of word productions for parents predicts the child's vocabulary. It's not actually, for the co-occurrences, it's not actually, you measure co-occurrences across everything the mom says, and then you measure vocabulary across whatever words it is the kid knows. It's not saying how many times did they hear the word banana with a co-occurring object does it take to learn banana. And so when you look at the analyses of corpora or day-long recordings, the frequency of any individual object name are extraordinarily rare, okay? They just don't show up, okay? Now, that makes sense that they just don't show up in most of those things because language is bursty and context dependent. You're going to talk about spoons at breakfast and you're not going to be talking about them when you're at the zoo, most likely. So, but the thing is, you still have to have enough experiences of spoon to learn what a spoon is, okay? That's why Elizabeth Gorkin and I did the mealtime study to try to say, all right, let's get within a context, one that repeats a whole lot, and ask how much are individual object names, not how much naming in general, but how much are individual object names occurring? And they don't. They're all infrequent, okay? It's the nature of language. It's just the way it is.
And then what about the age piece, right? So a 6-month-old, even in the clearest one-shot instance, isn't going to learn anything in the lab in 6 minutes. Maybe not even a 12-month-old will, but we know 18-month-olds
Yep, they're not going to learn. Here's our view. We think we can make them learn because you need persistence. You need persistence of those memories, and you need the multimodal context. And we're not going to do it by slides, and we're not going to do it. We're going to do it by multimodal context and persistence. That's what we're actually collecting the data now. Okay.
Great, thank you.
They will.
Thank you very much. And I think, unfortunately, we are out of time. Now, the questions that are still in the chat, from what I understand in the Q&A, I think those will be posted to the discussion segment for this talk. So I hope people can continue the discussions and the questions. Because now I would like to invite the next, actually, we have to thank our speaker. I'm sorry, I'm so nervous about running this. So let's thank Linda for the thought-provoking talk and the audience for their questions. Too bad we virtual claps. And now I would like to invite the next speakers to share their screen. So Curlin Kwam and Dan Swingley for the second talk in the session, entitled English Learning Children's Processing of Salient Phonetic Distinctions Varying in Phonological Relevance for Word Identity. Okay. I think whenever you are ready, you should be all set.
Thank you. Processing spoken language requires attributing only some types of phonetic variation to lexical distinctions. And children learning an intonation language like English must rule out pitch contour as lexically contrastive, attributing pitch variation to other sources like stress or phrasal intonation. So in English, pitch is not used to contrast words as it is in tonal languages like Mandarin. So if I say in English, referring to this, this animal, if I call it doggy with a rising intonation, or if I call it doggy with a rise fall intonation, I'm still referring to the same object or the same concept. So children need to recognize the word despite this variation and disregard pitch variation at the level of word learning or word recognition. But in English, children still need to attend to pitch for other purposes or other functions. So one example is to distinguish questions from statements. So if I say, you like the doggy, and you like the doggy I'm using those same intonation contours again, but now they're communicating information at the phrasal level. And pitch in English also indicates phrase boundaries, cues the location of lexical stress, and conveys emotional content. Our motivations in this line of work is to understand how children learn to correctly interpret readily perceptible phonetic variation. This question has implications for development of the lexicon and for acquisition of prosody. And for English learning children, the developmental time course of this learning is still somewhat unclear given conflicting prior findings and use of different stimuli across studies. So I'm going to highlight just briefly two different sets of prior work. The first couple studies I'll highlight use a fairly rich word teaching experimental method where you teach a new word and then you test children's recognition when the pitch contour is changed, comparing that to when the original word is presented or when the vowel is changed. And so a couple of studies using these richer word teaching methods have indicated that children at 18 months, this is work by Singh et al., seem to detect a change in the word's pitch and a change in the word's vowel. But at 24 months and 30 months, work from Singh et al. And our a 2010 paper that we published indicates that children seem to be following English phonology. So they're detecting a change in the word's vowel, but ignoring a change in the word's pitch. Another set of studies have used the switch habituation method, where children are habituated to two word picture pairings where the words differ in their tone. And the question is whether children notice a mispairing of the word and the picture. And so that line of research has shown a slightly different, or work with this method has shown a slightly different developmental trajectory, where at 17 to 19 months, work by Hay et al. And Burnham et al. Has shown that children do not seem to detect these mismatches of the pitch and the word. And it's only younger children at 14 months who do detect those mismatches. However, more recent work by Hay et al. Has indicated that's only the case when one of the tones is rising. So there are some nuances to the prior findings having to do with which particular intonation or tonal contours are used and which experimental method is used. The goal of the present study is to clarify the developmental time course of interpretation of readily perceptible pitch variation by testing children at different ages with consistent stimuli. So here we tested the pitch and vowel contrasts that we had used in the 2010 paper we previously published. So in experiment 1, we tested 3 to 5-year-olds who are learning English, 35 children. And we used one of these more richer word teaching methods to teach a novel word and then test interpretations of mispronunciations of pitch and vowel. In experiment 2, we tested 37 24-month-olds in the same word teaching method that we used in experiment 1. Then in experiment 3, we test 64 18-month-olds. And these are also English learning children. But with the younger age, we use the switch habituation method to teach 2 novel words that contrast in pitch or vowel. So first I'll show you the results from experiment 1 with the word teaching method with preschoolers. Again, we tested 35 children and we taught them a novel word on a screen in a story. And each child was tested on mispronunciations of both the word's pitch and the word's vowel. The procedure has 3 phases. So in the animation phase, there's a monkey playing with toys and children hear the word pronounced with a consistent pitch pattern like Debo 10 times. Then in the next phase of teaching, we ostensively labeled the word 12 times. So they heard that same Debo pattern, but the object was the only thing on the screen. And then in the test, they heard the original word Debo, or the pitch change Debo, or the vowel change, Dabo. Here's a video of the animation phase.
Once upon a time, there was a very friendly monkey. One day, Monkey got 2 new toys for his birthday. Monkey got one toy that looked like this. And he got a Debo. It looked like this. Monkey was very excited and wanted to share his toys with his friends. Then along came his friend Ducky. Monkey said, "Hi, Ducky. Let's play with my new toys. This is my Debo. Would you like to play with it?" "No, thanks," said Ducky. "I don't want to play with that." "A Debo? No way." "Okay," said Monkey. "Well, this is my other toy. Would you like to play with it?" "No," said Ducky. "I don't want to play with that toy. No way. I want to go float in the pond. Bye-bye." Once upon a time, there was a very...
Okay, so that was just a brief clip of the animation phase. Then in the ostensive labeling phase, again, children heard the Debo object labeled 12 more times in sentences like, "This is a Debo. That's right. Look at the Debo, the Debo." And then they also saw an equal number of distractor object trials where this distractor object was presented but not labeled. Then in the test phase, they saw the two pictures on the screen at the same time, the object labeled the Debo and the distractor. And then they heard these three different variants of the word. So the trained standard, "Where's the Debo?" was presented 8 times for preschool children. And then the intonation change, "Where's the Debo?" they heard in 5 trials. And "Where's the Dabo?" where the vowel was changed, was presented 5 times. And here are just some images so you can see the pitch tracks for the rise fall contour and the low fall contour. And I want to mention that this presentation of these contours in the training was counterbalanced across children. So some children were trained with the low fall contour. So children were seated on their parents' lap in front of a monitor that was displaying these pictures. There was a familiarization phase where the pictures were visible, then the speech would start to play, and then the pictures would go off. There'd be a bit more time with the pictures after the speech, and then they would move to the next trial. And I just wanted to highlight for children, we use the typical analysis time window of 367 to 2000 milliseconds after the onset of the word Debo. That's the region that we're particularly interested in to see the proportion of the time children are looking at the target object. And so we then coded children's videos frame by frame offline to determine where they were fixating on the screen in a way that was time locked to the presentation of the target word. So here are the results for experiment 1, the looking patterns for preschoolers. And again, we're averaging fixations to the Debo versus the distractor object. So we're showing a fixation proportion. We're averaging that over that time window, 367 to 2000. Here we can see they're looking responses to the original pronunciation in that dark blue bar in the center, to the pitch mispronunciation, the light green bar on the left, and then to the vowel mispronunciation, the red bar on the right. And then these gray box plots indicate within subject difference scores. And so what we see is that children at preschool age did not respond to a change in the pitch, but they did show a very robust response to a change in the vowel. So this is consistent with English phonology. Okay, so in experiment 2, we tested 24-month-olds in a very similar procedure. 37 English monolingual 24-month-olds were included in this study using essentially the same method as experiment 1. The only real difference was that we tested responses to the mispronunciations in separate children. So each child heard either the pitch mispronunciation or vowel mispronunciation test trials. This was due to more limited attention span in younger children, and it allowed us to have more mispronunciation trials in a given condition. So a child heard 8 original pronunciation test trials and 8 mispronunciation test trials. So here are the results for 24-month-olds. Because the mispronunciations were tested between subjects, children who responded to the pitch mispronunciation are shown in the left plot, and the vowel mispronunciation kids are shown in the right plot. And so the dark blue bars on the right side of each plot are showing the responses to the correct pronunciation. And the pitch mispronunciation is in the light green plot on the left of the left plot. And the vowel mispronunciation responses are in the red, shown in the red bar. And so what you can see is that at 24 months, children do not reliably respond to either mispronunciation type. So we don't see a decrement in their fixation of that Debo object for either pitch or vowel mispronunciations. So 24-month-olds recognize the word equally well across conditions, even when it was realized in a novel way. And this is in contrast to 3 to 5-year-olds who did not recognize the word when the vowel changed. So at 24 months, we seem to have caught children in a state where they had an underspecified phonological representation of this novel word. And recall that Singh et al., using a somewhat faster paced task, using Mandarin-like tones, found vowel but not tone sensitivity. So this finding contrasts with that prior finding with differences in the method and the stimuli. But this led us to use a less demanding task to investigate younger children's interpretations. We presented yesterday in a parallel session some data with 18-month-olds tested in the procedure used here. They did learn the word, but not as robustly as older children. And so here we used a less demanding task, the switch procedure, to determine whether 18-month-olds will detect differences between words in this less demanding task. So here in experiment 3, we used the switch habituation method, where children were habituated to 2 label object pairs, and each child was habituated in one of 4 conditions. In the first condition, children were taught 2 words that contrasted in their vowel, and there was low to no pitch variability. So they would see one object and hear, "This is a Vito." And they'd see the other object and hear, "This is a Vado," with the same pitch contour. In the second condition, children were taught 2 pitch contrasting words in the presence of low vowel variability. So this object might be called, they might hear, "This is a Vito." And then for the second object, "This is a Vito." So contrasting the rise fall versus the low fall pitch contour with the same vowel. In condition 3, children were taught 2 vowel contrasting words, but we introduced high pitch variability. So I'm going to try to play an audio clip so I don't have to say all the pitch contours live. So this is, children would see this object and then hear the following sentence or the following phrases.
"This is a Vito. Vito? Look at this Vito. A Vito."
And then children would see this object on other trials and hear the following.
"This is a Vado. Vado? Look at this Vado. A Vado."
And finally, in condition 4, children were taught 2 pitch contrasting words with high vowel variability. So this is the condition that's kind of the least compatible with, or the strangest maybe for an English speaker. So children would see an object like this and then hear the following.
"This is a Vito. Vado. Look at this Vado. A Vudo."
And in other trials, they would see a different object and then hear the following.
"This is a Vito. Vado. Look at this Vado. A Vudo."
So the 2 objects were being labeled with different pitch patterns, but there was also 4 different vowels being introduced within each of the test trials and habituation trials. Okay, so I've told you about the 4 habituation conditions, and now I'll tell you about the test phase of the switch procedure. So as is typical for the switch procedure, children were introduced to or tested with same trials and switch trials. So in same trials, they saw the same word object display as before. So one object was labeled Vito and one was labeled Vado, for example, just to use the vowel contrast with low pitch variability as an example. And then in the switch trials, the name and the object, those mappings were reversed. So now, thank you. So now this object is named Vado and this object is, this yellow object is named Vito. So we've reversed the pairings. We want to see if children will look longer when we reverse the pairings. So here are the results for experiment 3. What we're looking at here is the 4 conditions that I introduced. So the left plot is showing the conditions with low variability on the other dimension. And then the right plot is showing the high variability conditions. Within each of those 2 plots, the children learning pitch contrasted words are on the left and vowel contrasted words are on the right. Then within each of those 4, we see the leftmost data here are in the red are the same trials. And then in the dark brown next to that are the switch trials. And then the light brown is showing the different scores between same and switch. So essentially the switch looking minus the same looking. And what we are interested in is whether children are looking longer in switch trials than same trials. And indeed, that's what we find. So we found an overall longer looking in switch trials than same trials. And that held regardless of the variability condition or the phonological contrast. And so just descriptively, the learning looks least robust for the case of vowel contrasted words with high pitch variability, but that there was no interaction that emerged in the statistical analyses. So in conclusion, we find that 18-month-olds can flexibly encode pitch variation as if it were phonological, at least in a short-term test like the one we used. We do want to mention that in other studies, 18-month-olds have not treated pitch or been able to learn pitch contrasted words. So this is prior work by Hay et al. And Burnham et al. We also found that 24-month-olds can know a word without having committed to a specific phonetic realization. So they showed overall word learning, but didn't respond to mispronunciations of the pitch or the vowel. Although there does seem to be some dependency on the task, because Singh et al. Found that 24-month-olds did show the more mature pattern of responding to vowels, but not pitch, which is consistent with English phonology. And they used a somewhat faster paced task. Finally, we found that preschoolers showed the adult pattern. And so this is convergent with our prior findings with children at 30 months and adults, showing that at these older ages, children and adults detect arbitrary vowel changes while accepting salient pitch variation. So to conclude, we want to thank the children and parents who participated in these studies. We also want to thank the members of both of our labs. And finally, we want to acknowledge our funding sources. And here are the citations from the talk for your reference. Thank you.
Thank you. I missed the virtual clap icon. Thank you very much for the presentation, and I'm happy to open the floor for questions. And as before, you can put your questions into the Q&A. And also, please indicate if you are a early career person or student so that we can prioritize those questions. And so the first question will come from Laura Morit, and I think she will ask it herself. So hopefully you can unmute, you will be unmuted shortly.
Yes, thank you. Very interesting data. And I also found your task really interesting. My question pertains to bilingualism in a tonal language in addition to an atonal language. This is a population that I've actually looked at in relation to their perception of lexical tone. So my question is, but using a different test than yours, of course. So my question is, do you think 24-month-old children who are exposed to a tonal language like Mandarin, in addition to an atonal language like English, would differ reliably in the switch trials and low variability condition, but not the high variability condition? Because if I understand correctly, they didn't differ, the English speakers didn't differ on those switch trials in the low variability condition.
So there's a couple of different pieces to your question, so I want to make sure I'm answering each piece and understanding each piece. The last bit of what you said, it sounded like you were referring to our data in experiment 3.
Yes.
Yeah, and so I just want to clarify that in the statistical analyses, when we ran an analysis of variance, we did not, and actually I think we've done multi-level modeling as well, Dan. We're still finalizing our analyses, but no, I think for switch, we've only done ANOVA so far. We did not find, we just found an overall learning effect in the switch task where children were looking longer in switch trials than same trials. And so we didn't find an effective variability. I think what you're probably remembering is that I just mentioned that in the case where children were learning vowel contrasted words, in the presence of high pitch variability, just descriptively, that looked like the weakest learning effect.
Yes.
But it didn't emerge in the analyses. Yeah. So I just wanted to clarify that.
Yeah,
but I think it is interesting to speculate on, it might be, there's some suggestive patterns in the data that suggest that perhaps that variability was introducing additional challenges. So getting back to the rest of your question, so you're asking about, I think you were interested mainly in 24-month-olds, but children learning a tonal language and who are bilingual learning a tonal language and an intonation language.
Yes.
And you're interested especially in the switch procedure?
Yes.
Yeah.
In the low variability as opposed to the high variability.
Yeah. Oh, and variability. Yeah. So that's a very nuanced case, right? Like you're interested in basically a particular experiment. We haven't ourselves run that exact experiment. We looked at variability with the 18-month-olds. When we looked at, when we did actually try to test 24-month-old English learning children in the switch procedure, but got less reliable word learning actually. In any case, whether it was vowel contrasted or pitch contrasted words than we did in the word teaching method that we showed here in experiment 2. So we're currently trying to look around to, there are a couple of studies we've identified that do test 24-month-olds in the switch procedure, but we're still trying to get a sense of whether maybe they're kind of aging out of that procedure and out of that method, and it might be a little bit less like easy to keep their attention, or it's possible that they're a little bit on the older end for switch.
Sure. And actually, I made a mistake there. I believe I was referring to the age of your data from that. So I think I got that wrong. I meant 18-month-olds.
You meant 18-month-olds. Oh, okay. Yeah. So 18-month-olds can be successfully tested in switch. So yeah, I think, so your question is then if we tested bilingual 18-month-olds, if they would be sensitive to the variability.
Yes.
Oh, that's okay.
Specifically with the tone. Yeah.
Yeah, that's really interesting. I mean, part of our goal with looking at variability was to see whether it would make any difference in terms of, like, our thought was that maybe it would help to show emerging phonological knowledge. Like, kids are willing, at least in our data set, kids were willing to pay attention to either of these dimensions, even though the pitch distinction is non-phonological in English. And so we were like, well, maybe if we add this variability, it'll really help show the difference, show that they do know that this, the pitch is fundamentally different than vowel in their language. But that wasn't what we found. We ended up just finding that the same pattern held again. So at least in terms of, we didn't find a significant effective variability. I did want to point you to the work of Leher Singh, who's done a lot of, she's published several studies with Mandarin English bilinguals. I collaborated with her on one with preschoolers. So it's a similar word teaching task. So it's not a switch procedure. But I know she uses the word teaching task a lot. I don't remember offhand if she's tested bilinguals in the switch procedure, but I wanted to point you to her work.
Yeah, great. I'll check it out, and I'm familiar with her work. So thank you.
Thanks.
Now we have I think we have time for one more question, unless somebody objects loudly. So Jeff Lids will ask the next one.
Hi, Carolyn. Great talk.
Thank you.
So you described the 24-month-olds as being less committed to the phonological representation. Can you say more about that? Do you mean that the representation is underspecified in some way, or that it's fully specified, but that they recognize that they're sometimes wrong, and so they're willing to back off of their representation more easily?
Yeah, thank you for the question. We got a similar question in our parallel session yesterday. So Dan and I have actually been emailing about it, and then I just I have a review article on variability that's just coming out now in Wire's Cognitive Science, and with Sarah Creel, and we devoted some of that review to talking about these distinctions. So, so it is something I've thought about a lot. I think there can be a lot of ambiguity in how to interpret these results. Like, what does it mean when a child doesn't respond to one of these mispronunciations? We see that lack of responding to it is much more likely in children than in adults. But it's sometimes hard to say what that means. It's been interesting to collaborate with Sarah, because she works a lot on studies of like accent adaptation in children. And so she comes at it from even though we have very similar research training, she comes at it from like a slightly different perspective, where she's thinking about like, well, it's good to adapt and it's good to be flexible. And so maybe sometimes it's actually good to be accommodating of variation. Whereas I've been coming at it from this mispronunciation detection perspective, where I've been saying, like, thinking of it as like, oh, it's always bad if you don't notice a change that's phonological. But for these very subtle changes, when you have that target object right on the screen, you know, it's not a like wild notion that you know, maybe somebody just misspoke, or you know, maybe there's some other explanation, accent variation, some other reason that they use this slightly different pronunciation. So yeah, so I think that's a really good point, and it's one of the things we have to speculate about when we interpret our results. And yeah, and Sarah Creel's work she's sometimes trying to tease these things apart, but we're certainly always thinking about ways that we can differentiate those explanations. Thank you.
Thanks.
Now, unfortunately, I'm trying to keep an eye on the time. I would encourage, if there's any remaining questions that we didn't get to, please post them on the discussion location for each talk. But let's take a moment now to thank both speakers in the session, Linda Smith and Carolyn Kwam, for their thought-provoking talks. I always feel terrible cutting off questions, but I'm hoping people can continue, because now we have a 30-minute break. We will reconvene at 4:45 Eastern time. And so I will see everybody then, and maybe we can go check out GatherTown and stuff in the meantime. Thank you, everybody.